everyone. Okay, so today we are launching more into solutions, and we're actually looking at the more mathematical side of solutions. After talking about what things will dissolve in water, now we're actually calculating a lot of concentrations of these actual solutions, usually involving water as the solvent. So briefly, we're going to look at qualitative concentration descriptions because we really don't talk about much beyond them being dilute or concentrated. Now remember that qualitative, that L, refers to the quality, right? So it's not quantitative, it's not a number, but qualitative descriptions. Dilute just refers to there being small amounts of solute in the solution. Very concentrated, and think of dilute maybe being orange juice, and concentrated being that can of frozen orange juice, or frozen concentrate that you can buy from the store and then add water to it. That is concentrated. It contains a large amount of solute for the solvent, and really there's not much solvent in there to make it freeze. So very concentrated. Now remember, and this is going to be used throughout this lesson, solution inside has a solute and a solvent. Okay, solute is what is dissolving in the solvent. So don't forget that, because these calculations that we're going to see are going to be really difficult if you forget those terms. So solution is made up of a solute, the dissolved thing, in a solvent, the dissolving medium, or the water usually. So we're going to look at 4 different types of solution concentrations. Each of them has kind of its own purpose. So the first one is for quantitative concentrations is percent by mass. Now percent by mass is going to look awfully similar to percent composition. So we've already really seen this. Remember, percent composition was the part over the whole times 100, all right? This is the same thing. The mass of the solute, which is part, divided by the mass of the solution, which is the whole. Remember, the solution is made up of the solvent and solute. Okay, so mass of solute divided by mass of solution times 100. Part over whole times 100. Here's an example. What is the percent by mass of an NaCl solution containing 17.5 grams of NaCl per 500 grams of water? Okay, so we need to figure out the percent by mass, and we know that it's equal to the mass of the solute. Well, we have sodium chloride dissolving in water. That means we're going to have 17.5 grams, right? That's how much NaCl we have. This is the solute. All right, divided by the mass of the whole solution. Well, the solution isn't just the water. The water is the solvent. The NaCl is the solute. So we need to add them together to get the full mass of the solution. So we'll have 17.5 plus 500 grams times 100. Okay, times 100 is just to put it into a percent. And what we get when we divide 17.5 divided by 517.5 is 3.38%. All right, so that's the percent by mass. Now our second type of quantitative concentration is molarity. This is one that we use incredibly often in chemistry. Okay, so this is it's abbreviated by capital M, not to be confused with that capital M that we've been using for molar mass in the last lab. Molarity is equal to the moles of the solute, right? Still have solute on top, but this time it's moles, divided by the liters of solution. Still have solution on bottom, but now it's liters. So mass over mass, moles over liters. And you're going to see that the unit will be moles over liters for molarity, okay? Question is, and here's what I want to show you. This is why this is so common, is because not why it's so common, but often in the lab, in chemistry lab, we have different solutions. Some of them are already made when we buy them. Some of them we actually have to add water to and make them. But you can see that they're listed right here, 0.5 molar of copper 2 nitrate solution, versus this looks very similar, and this is 0.1, where is it? 0.1 molar, all right? The more dilute one is a little lighter, all right? But that's the difference, is we're seeing molarities here. Okay, we're going to take a look at how we can actually dilute a concentrated solution to make it more dilute. So the question here, what is the molarity of a saline solution containing 0.9 grams of NaCl for every 100 milliliters of solution? Okay, well, we need moles of the solute over liters of the solution. We have grams of the solute and milliliters of the solution. Well, milliliters is an easy fix, right? We know we can just move the decimal 3 places to the left, and we get 0.1 liters, all right? That's for, oops, yep, that's right. That's how many liters we have. Now we need to figure out how many moles of the solute we have, moles of solute. Well, you know how to find moles, right? You divide by the molar mass. So I've already done that here for you. We're dividing by the molar mass of NaCl, and we actually get 0.0154 moles of NaCl. All right, now we can use our equation here to calculate. We have molarity is equal to the moles of the solute. We found that. 0.0154 moles of NaCl divided by the liters of solution. Well, here's my liters of solution. So we have divided by 0.1000 liters, right? And what we get is 0.154 molar. All right, so we can calculate the molarity, which is, again, very common, especially in a chemistry lab, and especially this is going to be very important in diluting different chemicals for your guys' use in a lab, because oftentimes we don't want to give you the most concentrated solutions because we don't want as vigorous of a reaction if you don't necessarily know exactly what you're working with or what you're doing. So, how do we actually use this molarity and dilute a substance or a solution to make it less concentrated? Glad you asked. All right, we're going to use this third concentration over here, dilutions. And this is how we make a solution less concentrated. All right, this is going to look like a gas law, actually, and the way we're going to solve it is going to be similar. We have molarity 1 times volume 1 is equal to molarity 2 times volume 2. So we can actually use this to figure out how to make a dilute solution. Our question here, what volume of a stock solution of 2 molar MgSO4 would you need to prepare 500 milliliters of 0.4 molar MgSO4, okay? So we have a very concentrated solution, 2 molar, and we want, or we have a very concentrated substance, 2 molar MgSO4, and we want 0.4 molar, okay? So we need to dilute it. We're going to write down what we have. Our stock solution is what we're starting with. That's the more concentrated. And M2V2 is going to be our diluted solution. So M1 here is 2 molar. We're looking for V1. M2 is 0.4. This is what molar we're trying to get to, what molarity we're trying to get to. And 500 milliliters is the volume of this 0.4 molar MgSO4. All right, so we're going to plug this in here. M1, 2 molar, times X, we don't know what that is, equals M2, which is 0.4, big M, times 500 milliliters. All right, now we solve for X. It's a pretty simple solving. Multiply these, divide by 2 molar on both sides. All right, and on our volume, our first volume, so the volume of that stock solution that we need is 100 liters. All right, so what we're going to do to make this is we're going to add 100 liters of that stock solution. But we want 500 milliliters of solution. So then we'll add water to the line. And we'll have 500 milliliters of our more diluted solution. All right, last one of the 4 concentrations is molality. And this is going to be very important when we're talking about calculating boiling point or freezing points especially. We're going to see that on the next board. Molality, which is little m, not to be confused with mass or meters, all right, is moles of the solute divided by kilograms of the solvent, which is usually water. Water is usually the thing that's doing the dissolving, the substance that is that things are dissolving in. So our question here: calculate the molality. All right, and notice this L, molality, not to be confused with molarity. I know it's confusing. Calculate the molality of a solution containing 50 grams of NaCl dissolved in 3 kilograms of solvent. Great. We have grams of a solute, but we need moles. We have kilograms of solvent. That's what we need. Okay, so we are going to solve this because we have grams and we need moles. I've already converted from grams to moles. Right? Same process as before, divide by the molar mass. We have 0.856 moles. So molality, little m, is equal to the moles of the solute, which I have here, 0.856 moles, divided by kilograms of the solvent, 3 kilograms. And we don't actually know here what the solvent is. We're assuming it's water, but because it doesn't say, I'm just going to write solvent. And we get a molarity of 0.285 molar, okay? So, little m for molar, okay? You could also write moles per kilogram, but we usually, or sorry, not molar, molal. Big M is molar, little m, molal, all right? Now, last one that we're going to talk about is not really a concentration, but it's using that molality that we just looked at to calculate boiling point and freezing point. What we're talking about now is colligative properties. Now, colligative properties are properties that depend only on the number of particles dissolved in solution. That number of particles we call the Van Hoff factor, and we abbreviate with an I. Now, this is actually pretty easy to figure out what I is equal to. I is equal to 1 for any non-electrolyte, so things that aren't going to dissolve or dissociate, that won't dissociate in water. All right, this is mostly molecular solutes, right? Molecular polar solutes. They're not going to dissociate. So here's table salt, C12H22O11. This is a molecule. It is a covalent compound, right? Not ionic. So we know that I here is equal to 1. However, for electrolytes that will dissociate, which is ionic compounds usually, I is equal to the number of ions or formula units, okay? So here we have NaCl. When this is dissolved in water, it breaks up into Na plus and Cl minus. There are 2 ions here. For CaCl2, now we have 2 Cl's and 1 calcium. This is an ionic compound. It's a metal and nonmetals. I is equal to 3. 2 Cl's plus 1 calcium. Now what this lets us do is calculate colligative properties, which are the common ones we talk about. The most important is vapor pressure lowering, which means the vapor pressure of a solution will typically be less than the vapor pressure of the water, just the solvent. Lets us calculate freezing point depression, which says the freezing point of a solution will be less than 0. Freezing point of the solution will be less than the freezing point of water. And boiling point elevation. The boiling point of a solution will be greater than the boiling point of water, which is 100 degrees, okay? This has to do with why we put salt in water when we want to make it boil faster. All right. Our way of doing this to calculate the change in temperature for freezing or boiling is, this should be delta TF. We have a constant, which is down here, freezing point constant, boiling point constant, times molality times I, okay? Calculate the freezing point of 50 grams of CaCl2 dissolved in 1 kilogram of water. Well, we need the molality. In order to get that, we need the moles of solute. We have the grams of solute, so I found the moles. Now we can find molality. We have 0.451 moles of the solute divided by 1 kilogram of water, so we get 0.451. All right? Then we can plug it into our boiling point elevation formula. So Kb is 0.52 degrees Celsius over molal. Our molality is 0.451. And there are 3 ions, so I is 3. And we get 0.704 degrees Celsius. Add that to 100, and the new boiling point is 100.704.